All right, hello physics class. We're just going to do a very, very short little lecture on power. We talked about most of the other stuff we already need to talk about. A lot of your time is going to be spent working on your packet as well as some concept builders, those links with the trophies. But the first idea here is power that I want to talk about. Okay, power, if you remember, is, well, not if you remember because we haven't talked about it yet, is equal to work over time. Okay, we know that work is equal to force times distance, or force cosine theta times distance, but we haven't talked about the rate that work is done. Okay, think about doing any amount of work. You could do it fast, you could do it slow. And like so many terms in this chapter, there's kind of a physics definition for what power means. There's a different kind of everyday explanation for what a term means. Now, power means having, in everyday language, means having influence, having control. But in physics, it means something very specific. It means the rate that work is done. So how quickly can you do work? Now, me and you climb up a flight of stairs. Or say I take that back. Say I walk up a flight of stairs, and then I say run up the next flight of stairs. Now, in both flights of stairs, I did the exact same amount of work. I did work by increasing my body's potential energy. I increased my height, so therefore I increased the amount of potential energy that I have. So what's the difference when I walked versus ran? When I ran, I did it very rapidly. Okay, I did that work quickly. Okay, so when you talk about big earth movers and tractors and front end loaders, that kind of stuff, backhoes, those are all big power equipment. You talk about horsepower in a car and that kind of stuff. They can do work much more quickly. Think about a car. This is a good example that I always like to bring up. Is say you take two cars, your normal, everyday, run-of-the-mill, kind of boring car, a Toyota Corolla, my wife's car, a Subaru Legacy. That just gets the job done, gets you A to B, nice, safe, doesn't do anything fancy. You take a car like that, you compare it to, say, a sports car. A Corvette, a Lamborghini, a Ferrari. Now, sometimes in car commercials, they always say, this car can go from 0 to 60 in 4.2 seconds. Now, every car, mostly, at least, can go from 0 to 60 miles per hour. Can a Toyota Corolla go from 0 to 60? Sure. What does it do to itself in that process? It gives itself, it's doing work on itself, by increasing its kinetic energy. The chemical potential energy stored in the gasoline in that car is converting to kinetic energy of the car. So the car gained kinetic energy. By gaining kinetic energy, work was done on it by converting energy stored in that gasoline. Then say you take a sports car like a Corvette. Let's just say it's the same mass as the Toyota Corolla. Corvette can also go from 0 to 60, but what's the big difference? It's going to go from 0 to 60 in a much higher rate of speed. Okay, it's going to be able to, instead of going from 0 to 60 in 7 seconds, it's going to be able to do it in 4 seconds or whatever it is. I don't know. I'm not a car guy. That's because a Corvette is more powerful. It can do that more quickly. It can gain that kinetic energy more rapidly than the other car, than the boring everyday car. And that's where we get horsepower from. Okay, a sports car might have a horsepower of 400 or 500 horsepower, whereas an everyday car might be between 100 and 200 horsepower. Horsepower is an alternative unit to the watt, but 1 watt is equivalent to 1 joule of work done per second. So you can have all kinds of scenarios which the same amount of work is done, but the rate that it's done is done at different rates. Okay, so powerful has to do with how quickly work is done. It's a pretty simple equation. Okay, and if you think about it too, since power is equal to work over time and work is equal to FD, I can't really write on this here. So again, if power, try to do this as neatly as I can, is equal to work over time, and remember that work is equal to F times d, and still over t. Now, if you look at that d over t, distance over time, what's that equal to? That's our equation for speed. So if we wanted to know instantaneous power, that would wind up equaling force times speed. And that's kind of another way of looking at So, how quickly work is done, okay? So generally, when you think of somebody powerful, you think of somebody, you don't think of, the biggest, heaviest, fattest person, the 300-pound guy that moves really slow. You also don't think of the 110-pound guy that is super fast. Think of like, say on, a basketball team. So you might have a point guard, really light, skinny guy, but he's very fast, he's very agile. Probably not the most powerful. You also might have this huge, ginormous center with a lot of weight. And he might not necessarily be the powerful, but it's maybe that, forward, that kind of guy that's pretty big, but also decently fast. Maybe a football player, maybe a football example is a little bit better. It's not going to be the quick cornerback that's, or running back that's, maybe it will be a running back, but a cornerback's really kind of light and they move very quick. It's also not going to be the huge offensive lineman that's 300 pounds. It's going to be the linebacker, maybe the running back, the guys that are pretty heavy, but also pretty fast. They're going to be the most powerful because they're doing work on their own body, okay? So it's determined by work and how quickly you can do that work. So if you're slow, that means your time's going to be large and power's going to be low. If you're a lighter guy, you're not going to have to do a whole lot of work on yourself. If we isolate this down to going back to climbing up the stairs, the really light person, they sprint up the stairs super fast. They're not going to be that powerful because they're so light it doesn't require a lot of work to lift them up a flight of stairs. But somebody who's really bigger and slow and they move up the stairs, they're not going to be super powerful either because it's going to take them so long to climb the flight of stairs. But if you're a decent size and you're pretty fast, that's a person who's going to generate the most power by climbing up a flight of stairs. I keep talking about the flight of stairs because that's going to be a lab that you're going to do in the last week with Mr. Lovett, where you're going to go out in the hallway and climb a flight of stairs to determine your power, both in units of watt and in the units of horsepower. And that kind of does the same thing here. So if you run up the flight of stairs, you're doing work more rapidly. Okay, whereas if you walk up a flight of stairs, that's kind of more spread out. You are going to produce more power running up a flight of stairs because you are increasing your gravitational potential energy more rapidly. Again, the watt is equal to 1 joule of work done per second. A typical fluorescent light bulb has a power of 23 watts. That means it's emitting or using 23 joules of energy every second. Another familiar unit of power is the horsepower, HP. I mentioned that when we were talking about the cars. Well, horsepower is defined as being equivalent to 746 watts. Okay, 746 watts. Okay, now when we eventually do that lab and you can achieve over 1 horsepower, that would be pretty fast. That would be pretty good. That means you're pretty powerful. But most people will probably wind up being under this number. A few people might be over there. I don't know. It kind of varies. Depends on how accurate your timing going up the stairs is too. But it should be maybe plus or minus a little bit above or below 1 horsepower, depending on how much you commit to running up the stairs when we eventually get to that point. So again, human outpower is limited to about 1 horsepower. It gives you some different examples of power output: a stove, refrigerator, television, the human brain. Your brain emits a lot of power. I think I saw something like some incredibly high percentage of your body's energy output is all consumed by your brain. That's why you're more tired when you're studying for finals and you're exerting yourself. That's why you're also more tired. You may be more hungry when you're really stressed out and your brain is occupied by problems at home or relationship issues or some other stressor that's been put on your life, because that's hugely taxing on your brain because your brain consumes so much of that. So that's why it's important to relax a lot of times, because it's when you can relax your mind and do that kind of thing, some people meditate and that kind of thing, and that kind of relieves some of that energy loss, that energy consumption by your brain when you can just kind of relax and do that kind of thing. This, what I already said, is that an alternative form of power, we break this down like this, is just force times speed. But that would be more indicative of a instantaneous power rather than an average power. And that is the end of our slideshow. There will be assignments from our work packets. The work packet is pretty extensive. It's got, I think, 20 pages here. We're not going to do all of those, of course, but as they usually are, they're a good little review and practice for us as we move forward. So good luck with all that, and that should more or less, other than a few reminders and refreshers of stuff, that should be the majority of the notes on work, energy, power, conservation of energy, and that entire chapter. We'll be getting ready to test after I get back. I will be back in class on January 31st, but the test will not be too far after that time.